Thank you very much for inviting me to this meeting, and I'm happy to talk about thyroid dose assessment and thyroid cancer based on the UNSCEAR Fukushima report, and a little bit something else as well. So today I'm talking about um, several points. My first one is after the accident, Fukushima Prefecture started large-scale thyroid examination of children under 18 with high-resolution ultrasound equipment with needle biopsy, which identified an unusually large number of cases. And some say that this is due to radiation from the damaged reactor. And they even say that the rate being 30 times higher of the background. Some others say this is due to the highly sensitive screening system. And the debate between the two is ongoing even now. So since radiation induction of cancer is dose dependent, I'll discuss this based on the dose estimates of UNSCEAR 2020 report. In addition, radiogenic cancer of Chernobyl accident has a clear radiation signature at the DNA sequence level. So I believe the current futile debate on the cause of Fukushima thyroid cancer will be resolved by the molecular analysis. Okay, the summary of Fukushima thyroid examination during 2011 and 2022. And Fukushima Medical University performed 5 cycles of thyroid examination. The first one started 2011 to 13, and second 14 to 15, and third 16 to 17, and 18 to 19, and fifth one is 20 to 22. And in addition, they performed the examination of 25 years old person who just been following this examination since 2011. And important point is this third one, and I'd like to just talk about this number of thyroid cancer. And the first examination is only 3 years, and then it identified 116, and second one identified 71 and 31, 39, 34, and so forth. And it's very interesting that this number is highest. The number of cancer identified are highest at the first cycle, although it's 3 years instead of 2 years for other cycles. Still, this number is very big. And then number goes down to 71 since the period to examine is 14 and 15, 2 years. So maybe one third will be just going down, but nevertheless, third and fourth and fifth goes they stay constant around this high number. And so the reason why I'm curious about this is this is a time, 2016 is a year which is 5 years after the accident. And if the radiogenic cancer is induced, usually cancer requires certain latency. And in the case of Chernobyl thyroid cancer, the incidence started to goes up just about 3 to 5 years after the accident. But Fukushima case, the number is high to start with, and that's very weird. But anyhow, that is a fact. And so this is a interesting point to consider. And also, one other thing is, Those response for all solid cancer of A-bomb survivors, atomic bomb survivors in Hiroshima, Nagasaki, the number of them are just 120,000. Age, this data is age at exposure 30 and incidence counted in 70. And then it goes up linearly, nicely. And one gray or one CWL is giving 50% increase, not 5 times increase at all. And 2 gray, then excess relative risk goes up to 1. And so it's this number 0.5, 1.0, 1.5 is kind of very modest when it comes to the dose. So risk of cancer is affected by many factors, so that it is difficult to confirm the statistical significance of radiation risk below 100 millisieverts. You can see this low dose area, points are scattered around, and epidemiologists say for the atomic bomb radiation that this range is too low a dose, so that it's very difficult to get the statistically significant increase. And this is a kind of point to think about. And then for the thyroid, the situation is worse in a sense. And Hiroshima Nagasaki's thyroid cancer case, those responses, they analyzed just 100,000 people, and age at exposure average is 10, and incidence counted is 60 years old. And thyroid cancer is assessed, and the dose below 200 milligray, they say it's impossible to say statistical significance or not. And for this analysis, 371 thyroid cancer were diagnosed during 70 years after the bomb, and excluding those with a diameter less than 1 centimeter. And so excess relative risk for 10-year-old exposure was 1.28 per gray. Again, very decent number. And if you take smaller cancer, microcarcinoma among thyroid microcarcinoma among survivors, and then these are probably analyzed from the autopsy case, biopsy case, and so forth. And then you can just say, well, less than 5 millisievert relative risk or odds ratio, I forgot, but it's just 1. And then just about 500, less than 500 millisievert, this odds ratio or whatever, excess relative risk or whatever, is 1.44, very small increase. This was odds ratio, I believe. Yeah, odds ratio. So it's also this increase is not statistically significant, but anyhow, there is a tendency of going up. Then compared with this dose I talked about for A1 survivors, the final dose estimate of UNSCEAR 2020 report is highest one is 21 milligray. 21, that's really small. So this, for me, this dose is too small a dose to raise the incidence of thyroid cancer. Yet some claimed the 30 times increase, and really outrageous number. And nevertheless, harsh exchanges are continuing for the cause of cancer even now. But such exchanges, harsh exchanges, can be resolved if radiogenic cancer has specific marker on which you can say, oh, well, this is radiogenic or spontaneous. And we just, since I'm a radiation biologist, so I just want to talk about this and specific marker of radiogenic cancer. And radiation comes into the cell and damages many molecules, especially DNA. And DNA, maybe base is damaged, or this phosphate, this connection is cut and single strand break, or two of them are cut and double strand break. There are three types of damages, and base damages are more or less repaired well, but can give rise to point mutation. And single strand breaks are correctly repaired. And double strand breaks are repaired by non-homologous end joining, resulting mutations like deletion or gene fusion. And these are relatively specific to radiation. And so this is a kind of case of radiation damage and mutation. And what is this non-homologous end joining and radiation-specific mutation? Think about gene A, B, C, and let's think that about the case that gene A is damaged by radiation on its base, and that's gonna eventually be fixed as point mutation or maybe repaired completely nicely. And in the case of cells, especially cycling cell, you have double strand breaks taking place here and gene B and gene C and here. And these are just removed and then joined, these two ends are joined together to make gene fusion. Or maybe deleted part is just deletion. And this is the way non-homologous end joining repair functions. So thyroid cancer is usually caused by either by point mutation or gene fusion. And radiogenic gene fusion can be verified by the DNA sequence of the fusion point. And so this point you can sequence and you can see that these ends are just blunt ends are just joined together and very meticulous way, and many genes are just involved. And if you find this kind of sequence and the sign of non-homologous end joining, you can say quite safely that this is due to radiation. So such studies been done by on the Chernobyl thyroid cancer, and this paper I'm referring to is led by the study led by Dr. Chanok of NCI, and he counted gene fusion event. I mean, Chernobyl cancer, thyroid cancer was taken and DNA analyzed, and ratio of gene fusion mutation versus point mutation, and which mutations are more often for Chernobyl cancer. And then depending on the milligrade dose, it goes up, ratio goes up. That means, higher the dose, larger the number of gene fusion event taking place. And also, these gene fusion are caused by just a non-homologous end joining, which is a sign that the radiogenic damage can be repaired that way. So the rate of these two mutations goes up by radiation means, this is really the radiation doing the job. So I think that based on such experiment, I'm sure a similar experiment of sequencing the end joining site of Fukushima cancer will resolve the debate. And I'm sure that eventually some of the molecular biologists will be tackled on Fukushima thyroid cancer. And some of them already identified the point mutation, but this thorough sequencing are still missing. And so it's a time which we need, and also probably research money as well. But anyhow, I end my talk here. Thank you very much.